Coding and testing. This is part 4 out of 5, so we have a 5th one afterwards. I will go very quickly through the testing ones, especially because we've done some testing yesterday. I will only review the concepts and the general approaches, but I want to spend some time on the coding aspect, not so much to review the individual vulnerabilities that you can create by coding. This is something we've addressed yesterday, and I've learned you've done this in another exercise as well, but more which ways of thinking you should adopt, which elements you should have in mind for being on the safe side when coding. Okay, a vulnerability refers to a weakness in an application. Attackers try to find such weaknesses. A typical reason is insecure coding. Elements are backdoors in the code, execution of commands, bypassing authorizations. Exploits are vulnerabilities with working and fully implemented attack. So an exploit is software or some kind of maybe also just a recipe to exploit make use of a vulnerability. A zero-day exploit is an exploit that is not yet known to the vendor, to the manufacturer of the software. So it's 0 days known. Cross-site scripting. Now we've done this, so this is something we could skip. And this is an example which is a little bit older, but there are different sources for classifying vulnerabilities. And I've mentioned 3 here, the OWASP top 10 that we've dealt with yesterday, but there are also the 7 pernicious kingdoms, which classifies vulnerabilities to certain types of errors that you can make as a developer. You can read them if you want. And you have the 19 deadly sins of software security. It's also from Gary McCraw, the author that I mentioned earlier, who was at Microsoft. And as you can see, you can map them to each other. So there's always some value in looking at new vulnerability type classifications because you learn things, of course. But basically, when you're using one, you're on the safe side. So it's good to use such a classification scheme to understand things. And I personally like very much the pernicious kingdoms, and I think it is possible to make them even more simpler, and this is something I would like to show to you, namely this one. We have so-called vulnerability patterns. They are the counterpart to the design patterns on the coding side. And the vulnerability patterns describe a more generic categorization approach and help to explain conceptual difficulties to make software secure. And you can actually group them in these 4 groups. Every vulnerability that you create or that one creates at coding level, not at design level, at coding level, is one of these 4. And it's either insecure input and output handling, insecure memory management, insecure handling of race conditions, and insecure handling of authorizations and resources. So I think the only one that needs to be explained is the 3rd one. The other 3 are pretty easy, I think. Input-output is clear. We discussed this yesterday, lengthy. Handling of authorizations and resources is the same. So you don't manage you don't keep track of who should access what, and the coding is not matching the expectation at a business function level. Memory management, this applies to languages where you can escape or where you can manipulate memory storage, like in C, for example, or C++. And you can create buffer overflows, or you can let attackers create buffer overflows. There's one, the last number of attacks on, say, SSL, there was an SSL attack, And a shell attack, a bash attack, that is very widespread actually. These were memory management problems because the actual low-level functions for SSL handshaking were written in C, and the developer forgot to limit the size of the buffer that is accepted. And so people could actually extend information, attackers could send a bigger information into this buffer, and that would override the rest. Or alternatively, you set the pointer to read as long as this, although the parameter was only this long, and then you could access information which is standing there to read out confidential information. So this is insecure memory management. And we have insecure handling of race conditions. This is a problem when you're making available a programming resource like a method or a class available to more than one user being another class or a program or everything similar. And if they can access, if they in principle can access this resource at the same time, but for the logic of implementation to be executed in the way that is secure, you need them to happen in the correct order. But sometimes during the optimization of coding during, say, for example, compilation, it's possible that the order changes. Specifically if you're programming concurrently. So if you have different programs, different web services, for example, starting at the same time, accessing resources. And then this is called a race condition. So who is going to access this information first? So they're having a race, different services want to access the same resource on a programming level, and it's important that the order of the race, of the result of the race, is the correct one. But you cannot if you do not pay attention that it's happening in the right way, it may happen that the order changes, and that would be leading to an exploit. That would be is a vulnerability that can be made use of. How to fix this? Well, it's a very simple approach. It's called semaphors. A semaphore implementation, you probably learned this in second semester or so. It's a standard mechanism for protecting resources. And if you have a semaphore, then you cannot have a race condition. So there's just, in many languages, using semaphores solves the problem immediately. Okay, I explained all this. You can read this. Time of check, time of use. This is the race condition. There's an example here. A web page contains read-only elements. Content of those elements refers to user data. A malicious user can guess data of another user and submit this data. The program was planning this field as read-only, as might be the case in a hidden field, and no second check is being performed upon access to the resource specified by the user data. Yeah, you can read this for more detail. Yeah. So, coding practices, these are now the recommendations that they match now the vulnerability patterns, and so you should think about these important elements. First, validate every input. If you got some input, always perform validation against what you expect. Don't be lazy at this point. Don't accept more that you would actually really expect. If you expect a 16-digit number for a credit card, only accept numbers of length 16-digit. Not 17, not 15, not whatever, right? Output sanitization. If you are receiving content from an untrusted source, that you make part of some sort of display or shall be in some form executed on a web page, then it should be sanitized. That means you should only interpret this as text and not as potential programming code. So it neither should be available to be executed in JavaScript nor in PHP, whatever. So it should only be text. Use secure functions. So if you have programming languages that have include memory management like C and C++, use always the secure versions of the functions. Specifically in C, there are, for every, say, insecure functions of memory management, you always have a secure version. Use that secure version, right? Like, for example, copying strings. You could copy strings with strcpy, which uses a buffer of limited size, whereas with strcpy you need to give the size of the buffer that you copy as a parameter. Of course, also use secure programming languages. So yeah, Java in general is better than C in terms of security. Atomic functions and semaphors. The race conditions appear in implementation of business processes, but they can also be necessary to be handled at system level. So console log into early Linux systems. After logging in, enter escape many times, and you got a root shell. If you're fast enough, that was a trick in the earlier days. It doesn't work anymore today, but that actually I managed to do this when I was at university myself. Something we did. It was fun. I mean, we couldn't do anything with the root access as students, because they would have been discovered immediately, but it was just fun to be the first one. Be aware of race conditions, especially in web applications, because web applications are stateless. The problem of web applications in terms of security is not only because the state management, you need session management, but also that you do not know which request came first. So if you have a sequence of activities happening on the same data, and if an attacker could actually try to come before you, so to manipulate the process. Implement atomic functions that execute defined activities without the possibility to manipulate the corresponding data during this activity using other means, and if not, use semaphors. Use least privilege also at coding level. Least privilege in general is for authorizations, so that people got as less authorization as possible, but the same applies for coding. So you should use minimal access and authorizations and even minimal visibility in the functions. This is interestingly contradicting good practices of good software quality. In software quality, typically you learn that you expose and describe the methods and elements as much as possible, so that it's easy to understand and easy to follow. In security, you would say, there's no need for publishing private methods. Why should I do this? Well, it should really keep private. Right? Don't publish this. Secure error handling. If errors are not handled appropriately, the application can fall back into an insecure state. Even more, attackers might try to force an application to fall back to such a state. Therefore, establish and enforce secure error handling, strong error handling. So you should be able to escape, throw exceptions whenever it's possible, especially in Java. Explicitly specify the error handlers and applications, disable unneeded functions, remove the standard debugging packages of productive systems. Secure coding tools, use tools for secure coding. So you could integrate this into your development lifecycle. So I don't know whether this is actually the case in the organizations you're working part-time, when they have established software development processes with tool chains with a set of tools that are used, say, for example, for development to production speed up, then it's worthwhile thinking about whether I could also integrate tools in that chain that do some static code analysis, for example. That are all the things that we spoke about. Most of them can be identified using patterns, and will then, if a static code analyzer is used, will be highlighted. There are some very prominent code analyzing tools. The most prominent one is from Fortify. I don't know if you know that name. Fortify is the name of the company. Fortify produces code centers for all major languages. They started with C, they have things for Java, they have things for Python, they have things for SAP, they have things for web applications using PHP and SQL. So there's lots of stuff available from them. They have been acquired by HP. Now, if you look up them, you will find HP Fortify is their claim. And there are many, many more. So if you look at Fortify and compare, or Fortify and look at other vendors, you will find a bunch of tools that help you doing some static code analysis. There's, for example, check marks, or there's another prominent one, check marks. No, I'm missing them now. It's speeding too much up. And I would recommend to look at to implement such a tool as part of your coding chain, of your tool chain for coding. There are some open source scanners as well that are not as good as the supported. The support is better from the closed source scanners, but still it's a valid point. And another recommendation: most integrated development environments offer some sort of basic security checks as well. So if you are using Visual Studio, in Visual Studio you can turn on a number of security checks. Even this is also very helpful. Or if you're developing in SAP, SAP has its own check mechanisms implemented as well. Yeah, okay, we don't need this. Okay, I spoke about this as well. Good, this is for coding. So let me quickly go through the testing and we'll make another exercise. So in principle, testing is easy. There's no real challenge testing. The problem with testing is that it's tedious and boring, and nobody wants to do it. Testing, oh, I know. So, but nevertheless, if you document testing well, and if you manage to automate your tests as much as possible, you would gain a lot out of this, specifically for security. So therefore, I would urge you, although it's boring, to execute tests for your software, specifically security tests. I would like you to describe test cases. This is one example for a test case list, but you could also describe it in the fashion that you want. So you look up the internet, or maybe you have had testing and quality assurance in another lecture. Then you use that. That's fine for me. I don't care regarding the format. Testing shall be done during development, so as easy as in development, but also during deployment and some during maintenance. So all major German banks today perform security tests of their installed software. They're running software every night. So every night, it's not they buy some tests and they do it once per year. They have installed a standard testing framework and they run all their applications through their testing environment every night. It's parallelized, so it's always looking at something different, but it's running every night. The easiest thing to get to test cases in security is, first of all, to use your acceptance criteria. So, one request for me for the homework is transform your acceptance criteria, which are written at some high-level description language, into a real test case, into a description how you would actually give this to someone else to be able to execute it. So a test case is a complete description of what is to be done, what is to be prepared, what is to be done, and what is to be observed, and what is to be documented. And it should be so explicit that I could give you this list without talking to you, and you would perform the right test. Right? So it should be clear. You should give this to any student of first semester computer science. Here, I have a part-time job for you. Execute this test, please. And it should be foolproof. So the error would be on your side. If it's not well documented, then it's your problem, it's his problem. Okay? And therefore, from threat model to security test plan. How to come to good security test cases, moreover, you could actually decompose the application into fundamental components. You can identify component interfaces, and every interface could be tested. You could identify the data which is accessed by each interface. This relates to the data flow diagrams we had earlier in the threat modeling. You could also use data flow analysis for code analysis. It's done by some of the vendors as well. So, for example, for Virtual Forge, for SAP, there's Virtual Forge, a company out of Heidelberg that does data flow analysis in code. So it doesn't describe the diagrams in design, but they're scanning the code and actually constructing a data flow diagram, and from there they will actually find new vulnerabilities at a logical level. Create a test case for each identified attack vector, that's the threat modeling approach, and inject mutated data. This is with fuzzing, and we'll see that later. So there's black box testing and white box testing. We've spoken about this already. I will skip this. You can read this for more detail. You could use, that's what we've done yesterday. You could use some scanner, or you do it manually also. And there's fuzzing. There's also something I spoke about yesterday. So you could actually try and use a fuzzer to test your own application. A fuzzer is a combination of a structured testing approach together with some randomization of parameters, where the randomization happens within specific meaningful boundaries. So very interesting approach. You could perform reviews, so code reviews, of course. You could look at the code jointly once it's done to verify that there's nothing else there that was actually expected. You could do walkthroughs with the authors and inspections. And finally, you should write a test report that should contain the information which basically says, okay, this software has this level of security and this remaining number of vulnerabilities, and due to the risk we identified earlier, we either urge to correct this, or we recommend to be prepared in case that an attacker will find it outside once it's at customer side. So exercise 1. There's only one. Deduce from the threat modeling of your application 10 corresponding test cases. Not all, not for all, but 10 corresponding test cases from the threat modeling. In parentheses, maybe also would be a good idea from the acceptance criteria and define a black box test plan. So create a test plan how you would test your own application using black box. Which tools, how long, what you would look for, what is the expected outcome. Good? Okay, 5-minute break. 5-minute break. You didn't have a break. 5-minute break.
We didn't.
Yeah, you didn't. You didn't have a break. So therefore, 5-minute break. Because you didn't have a break. Your 5 minutes from earlier, you didn't have them. Good. On redémarre à 15. Une question? Ça fait 6 minutes.